We're continuing our work with inverse trig functions on this page of notes as we're looking at day 2 now. And we're going to see some overlap between what we're finding here in example 1 and 2 and what we did on the previous day of notes. So this will be the first topic we're going to cover, and then the second topic will be those story problems that you see down there, the application problems, where we're going to be calculating the reference angle in our triangle. Here we're starting off with these problems which don't look like triangles, but let me show you they really are. Because remember, if you have a sine or tangent or cosine, those can always be thought of as the ratio of two sides of a triangle. If we back up to the previous day of notes, you'll see that we had some examples where the diagrams were already provided to us, and we could set up a ratio of two sides to create that ratio and then even represent that so that the reference angle was isolated. That's our inverse trig function right there, right? And so what we're going to do is the same thing, but we have to create our own picture this time. So on today's topic, we're taking a look at example 1 and 2. They're really quite similar in that what we're doing is we're using the given information. What you're looking at here, the parentheses, that's the given information, as the ratio of two sides of a triangle. And because it's represented as arctangent, that's really the inverse trig function, meaning if you could draw a triangle using this given information, which is the ratio of two sides, then that will result in a very specific reference angle. So remember that the answer to an arc sine, or the answer to an inverse sine, is always going to be theta, right? The answer to arctangent, or the answer to inverse tangent, is always going to be theta. Now, we're not calculating that theta. We don't really need to know what that angle is, but it's just going to be a placeholder on our diagram. And then once we get that information, then we'll proceed to finding the cosine ratio of two sides of the triangle we're about to create. All right, so let's start off with a small sketch. And here we have our reference angle that we're going to be identifying here in just a moment. There's my right angle. All right, so we know this is the adjacent leg. This is the opposite leg opposite to that reference angle, and of course your hypotenuse. So I've been hinting at two sides of the triangle here. Remember, if you just have x, think of it as x over 1. So your sine ratio is opposite over hypotenuse. So we'll put the x on the height and the 1 on the hypotenuse, and then we'll use our Pythagorean theorem to find the missing side. And so we have a squared plus the height squared, x squared, equals the 1 squared. And we'll use the a to represent this missing base. And when we take the square root of both sides to get a by itself, remember we cannot simplify the 1 or the x squared, meaning we cannot take the square root of that because these are not factors. Only if they were being multiplied together could you simplify that radical. So what we're doing is we are representing the third side of the triangle not with a specific value, but in terms of x, meaning we're using our knowledge of the height, which is just a variable, as a way to describe how the base compares to that height and to that hypotenuse. Now that we have all three sides, we have a way to say, okay, we're not actually calculating what this reference angle is. We don't have a size. We don't have a measurement. But with these specific relationships between the sides, we can now say, okay, this is fixed. It's fixed in the sense that our variable is fixed at being the height of x, or the base of root 1 minus x squared. Now we can take the cosine of that reference angle. And the reference angle is just referring to the diagram that we just drew. That reference angle saying it belongs here in this triangle when you have the height of x and the hypotenuse of 1. So we know the cosine ratio is adjacent over hypotenuse, so we will take the adjacent side length and set that over the hypotenuse, which of course is just 1, and that's your answer. So when you're looking at this notation, you're saying my final answer will be the cosine ratio, but we start with what's in the parentheses, using that pair of sides to create the ratio given to us, and kind of working outwards from there. All right, let's try that again. Here's part B. We're going to start with what's in the parentheses. We want the tangent ratio, which is opposite over adjacent. Right, there's my reference angle, so let's label the sides. Here's my adjacent leg, opposite leg, hypotenuse. So tangent ratio is opposite over adjacent, so the x goes on the height, the 2 goes on the base. So again, let's use the Pythagorean theorem to find the missing hypotenuse. So a squared plus b squared equals c squared. I'll write it as 2 squared plus x squared equals c squared. You'll notice we have several variables in here. Don't get confused on which one we're trying to solve for. We're not trying to solve for x. X is just how the height is represented on the triangle. We're trying to solve for the hypotenuse, and that's the letter c. So we're going to get c by itself by taking the square root of both sides. And this is my hypotenuse, which will be the square root of 4 plus x squared. Again, you cannot take the square root of 4. You cannot simplify the square root of x squared because of the addition sign. Only if they were being multiplied could you simplify that. So let me put that information on my diagram. The square root of 4 plus x squared. Now that we have all three sides, we can write any ratio we want. We want the secant ratio of theta. Now in this case, this theta is referring to this diagram, not the old diagram. Even though we don't have a specific number, that theta belongs here in this picture. So we can say, let's take the secant ratio of this particular diagram. So we know cosine is adjacent over hypotenuse. And this is the reciprocal of cosine. So we want hypotenuse over adjacent. And there's the result. Example 2 is almost exactly the same. The notation is represented, or I should say presented in a slightly different way, but it's going to give us the exact same information. It's going to give us a ratio of sides. And with that, we're going to make a triangle. And then we're going to find a new ratio of sides. It's saying, what ratio should I have? I should have the side ratio. What ratio am I starting off with? I'm starting off with the ratio of 3 over x. So we have to start here, of course, and then we'll figure out what goes in the question mark to fill in that blank. Here's my triangle. Labeling the sides, adjacent leg, opposite leg, hypotenuse. Cosine ratio is going to be adjacent over hypotenuse, so the 3 goes on the adjacent leg, that's the base, and the x goes here on the hypotenuse. So again, we need the Pythagorean theorem to find this missing side. I'll go a squared plus b squared equals c squared. So 3 squared plus b squared, b is what we're trying to solve for, equals the x squared. That's a 9, subtract 9 from both sides. And then when you take the root of both sides, the missing b, the missing height, is root x squared minus 9. So now that we have all three sides, we could write any ratio we want, but here there's asking specifically for the ratio that would belong to the sine ratio. So just kind of rewriting this here to give myself a little bit more space. Arc sine of, we'll take the question mark out of the parentheses and we'll put in our ratio. Sine ratio is opposite over hypotenuse, so we want the root x squared minus 9 on the top and the hypotenuse of x on the bottom. So in these types of problems, we're not solving for a specific x, we're not solving for a specific angle, but what we're doing is we are representing ratios. Right? So ratios, depending on whatever ratio they're asking for, we want the triangle first so that we can figure out which two sides to use in our ratio. So that's topic number 1 in this day. Now we're going to transition to some of these story problems, and this is really geometry. It's nothing really new for us because we've seen it at some point along the way. We have encountered angles of elevations and depressions. Just remember that with both of these, when we're naming this particular kind of angle, there is always a horizontal line. I call it a reference line because it is from that horizontal that you will either look up or you'll look down. So if you look up, that's an angle of elevation. Here is your horizontal reference line from which you are going to look down. And that's your angle of depression. The issue with the angle of depression is that oftentimes, not always, but oftentimes the triangle that we're creating is here, where we have one side of the triangle on the ground, and we have one side of the triangle representing the height, and then there's your maybe sight line or your hypotenuse. And this is the angle that you want to calculate. You have to have an angle inside the triangle if you're going to use sine, cosine, or tangent, but the angle of depression is not in the triangle. And so that's a problem. I can't use that angle because it's not in the triangle. So you might remember back from geometry, if you have parallel lines cut by a transversal, then it turns out these alternate interior angles are congruent. So what that means is that the angle of depression, I'll call it alpha, is going to be the same size as this angle of elevation. Turns out the angle of elevation is equal to the angle of depression, and that's the angle that we could use because then it's inside the triangle. Or you could use this angle. Remember, these two angles are complementary. They'll add up to 90 degrees. So you could calculate this angle, subtract it from 90, and then that would give you your angle of depression. Or just calculate your angle of elevation, and then transfer that information here, and if you found one, you found the both. So let's take a look at these few examples. Here's example number 3. We have a 40-foot ladder that's leaning against the building. At the base of the ladder, 6 feet from the base of the building. What is the angle formed? So when we're trying to find an angle, that means we want an inverse trig function. So that means inverse sine, inverse cosine, or inverse tangent. So we're still using our ratio of two sides. So there it is for reference. There's your SOHCAHTOA. And we're going to figure out what two sides we have on the picture so we can then determine sine, cosine, or tangent ratios from there. Here's the ground. Here's my building. Here's the top of the building. Here's the bottom of the building. And that can be helpful because we're going to see some of these clues, like the ladder is 6 feet from the base of the building, right? So we want to make sure that we're talking about the base of the ladder. The bottom of the ladder is positioned to 6 feet from the base or the bottom of the building. So here's the bottom of the building. So that means we should have the bottom of the ladder, and that's going to be 6 feet apart. So this ladder is leaning against the building, and that ladder is your 40-foot ladder. And they are asking for what is the angle formed by the ladder, so that's this side here of the triangle, and the building, which is this side of the triangle. So they're talking about this angle right here. This is the ladder, this is the building, that's what they want to know. So that's the reference angle. Let's label our sides. We have the hypotenuse, which is, of course, opposite the right angle. We have these two legs. The building is touching the reference angle, that's your adjacent leg, and the 6 feet is on the opposite side, that's your opposite leg. And so we want to find a ratio that uses the 6 feet and the 40 feet. So that's the opposite, and the hypotenuse, that's your sine ratio. So sine of the reference angle theta is equal to this ratio of two sides, opposite over hypotenuse, 6 over 40. Since we're trying to find the angle, we want to get the theta by itself, and to get the theta by itself, we have to undo the sine. We want the opposite of sine. We want the inverse of sine, and we do that on both sides so that the sine and its inverse cancel out. That's how you isolate your angle. And then that's what we type into the calculator, inverse sine of 6 over 40. So make sure you are in degree mode. We don't want radians here. These story problems are often in degrees. So 8.63 is your answer. Now, that is not an angle of depression. Just keep that in mind. And it's not saying anything in this problem about an angle of depression. It looks downwards, but no. If it actually wanted an angle of depression, we would have had a horizontal reference line here. We would have looked down like so. Those would add up to 90 degrees. We could go 90 minus the 8.63, and that would give us our angle of depression. But this particular problem didn't actually make any mention of that. But we will see it here in example 4. Example 4 says, find the angle of depression. From the top of a lighthouse, 250 feet above water, to the waterline of a ship 2.5 miles offshore. All right, so here's my very, very tall lighthouse. Just kind of representing it right there with a very thin structure. Let's pretend this side of the diagram is representing the ground, like the beach, the sand, and then this side is representing the water, and somewhere out there is your boat. It says 2.5 miles offshore. And we have the height of this lighthouse at 250 feet. So pretend you are up here inside the lighthouse, and if you were to look straight out, this would be your horizontal reference line, okay? As if you were looking out in the sky. But no, you drop your gaze, so you are now looking down to the boat. That is your angle of depression, and that's what we're supposed to find. All right, so that's my angle of depression, and I'll just label that with a theta symbol. That's my answer. But we learned that these alternate interior angles are congruent, which means that the angle of depression is equal to the angle of elevation. So if we can find one, well, I found the both, and this is inside my triangle, and so I will use that as my reference angle. Here's the hypotenuse, here's the adjacent leg, and here's the opposite leg. Before we jump into the ratio of two sides, notice that we have two different units here. This is 250 feet, this is 2.5 miles, which means we cannot mix and match different units. Let's convert both of them to feet, and I'm going to do that work first over here. So we have 2.5 miles. Set up our unit conversion. We want feet instead. We want miles on the bottom, so miles will cancel out with miles. And 5,280 feet is equal to 1 mile. So in other words, we are multiplying these two numbers, and we get 13,200. And that's in feet. So now we use these two values in feet. We have the opposite and the adjacent. The opposite and adjacent, that's the tangent ratio. So tangent of the reference angle theta equals opposite, 250, over the adjacent, 13,200. We want to get theta by itself, so take the inverse tangent of both sides. So tangent and its inverse will cancel out. Our variable is by itself. This is what you'll type into your calculator. Make sure you are in degree mode again. And we get a very small angle, so I'm using a little extra decimal place there. That is the measure of the angle of elevation, which is also the measure of the angle of depression. So we found our answer. All right, we'll finish up with this last example here. This is another instance where we're going to be using an inverse trig function. So this time we have a 75-foot cell phone tower, and we want to find the angle of elevation to the top of the tower from a point on level ground 95 feet from its base. So here's the ground. Here's my tower. We're going to stand 95 feet from the base, right? So here's the top of the tower, here's the base of the tower. 95 feet from that puts us about here. And then we're going to elevate our gaze looking upwards. So we're drawing our line of sight to the top of the tower. This is the angle of elevation then right there. So I'm marking that as theta. So that's my reference angle. So here's my adjacent side, here's my opposite side, and there's the hypotenuse. I guess I need to put the 75 feet on here. That's the height of the tower, so that's the 75. So once again, we're using the combination of 75 and 95, which is the opposite leg and the adjacent leg. So opposite over adjacent is tangent. This is the tangent ratio. Tangent of theta is 75 over 95. Take the inverse tangent of both sides to isolate the variable. That's what we type into the calculator. And we are still in degree mode because it's another story problem.